All right. What's on the agenda for today? All right. Where to begin? So what? Last time we talked about gradient and directional derivatives. I do think it's worth kind of recalling just so that everyone's on the same page. So just as a quick reminder, the directional derivative of some function of x and y in the direction of a generic vector v is given by, I'm going to write it like this, dvf, and it's equal to the gradient of f evaluated. Oh, I knew I forgot something. The directional derivative of x in the direction of v at the point P, apologies, is given by the gradient evaluated at the point P dotted with the unit vector in the direction of your vector V. So that's the very kind of generic way of calculating a directional derivative. Or if your vector is already a unit vector, we write it as duf equals the gradient of f evaluated at P dotted with just good old u. And then there's another reminder, the gradient of a function. I should say of a function of x and y is given by just the vector of partial derivatives. But this idea is extendable to more dimensions. So if you had a function of three variables, which you'll see in 21D, the gradient would be the partial of f, comma, the partial of y, comma, the partial of z. So just to extend this, or if your function is a function of x, y, and z, or whatever your variables happen to be in the appropriate order, the gradient's just going to be the vector with that many components of partial derivatives in the appropriate order. So if x, y, z is written as your variables, then it should be fx, fy, fz. They should be in the right order, right? Whatever you think is the right order, that's the right order. Unless someone does something where they make things backwards or out of order, which is silly. No one should do that. Couple other things we said last time, which I think are really important. Thing one, the gradient vector points in the direction of steepest ascent. Or said another way, is the direction that maximizes the directional derivative.
That's fine.
Was that?
My own problem, I kept having to find like the maximum. But now I understand like why it was that.
Uh-huh.
Is that no?
Right. And so kind of if you had some level curves, like let's say you had some contour map, you're actually like hiking in the world and you're looking at a map and it looks kind of like this. the gradient, again, if we're thinking like, let's say this elevation is like 200 feet, 400 feet, 600 feet, 800 feet. If I'm trying to find the gradient at say like this point here, well, it's kind of funky the way I've drawn this actually. So right here, the gradient would be pointing that way because I have to cross this contour perpendicularly. But then if I kept moving, then my gradient would change directions and be pointed that way. So the gradient at a particular point is the vector that points in the direction that is perpendicular to your level curves. Welcome. So, yeah. Also, I should say, the last thing I want to remind you of is that oh yeah, the magnitude of the gradient is the maximum value of the directional derivative, which we talked about last time, because we talked about how this directional derivative equal to the magnitude of the gradient times the magnitude of your unit vector times cosine of the angle between them, right? That's your gradient dotted with u. The maximum this can ever be is just the magnitude of that gradient because the magnitude of u is 1 and cosine of theta is at most equal to 1. Let's see, let me see if I can find this question I'm looking for. No, I can't find the question I'm looking for. Oh, well. Sure. So let's look at some examples of questions we could ask about. So I will say, I kind of feel like a lot of these directional derivative questions are kind of contrived. Like they feel like you have to kind of work hard to make an interesting question. So let's say we have the following example that's very kind of just basic. So we have our function is given by f of xy is equal to xy plus y squared. And we want to first find the slope of your function, the slope of your surface at the point 3 comma 2 in the direction of the vector v equal to 1 comma 3. Really, this is just an application of remembering the formula and substituting in the appropriate values. So let's find all the things. We need our gradient, which is going to be the partial derivative of this with respect to x. So that's going to be y, comma, the partial derivative of this with respect to y, which is going to be x plus 2y. And then we actually need the gradient at the point we're looking at. So the gradient of f evaluated at 3 comma 2 is going to be the vector 2 comma 3 plus 2 times 2. Or in other words, it's going to be the vector 2 comma 10. Our direction vector should be a unit vector. So we're going to take our actual vector v and divide it by its own length. That's going to be the vector 1 comma 3 divided by the square root of 1 squared plus 3 squared, which is 10. And you can write it this way, or you can write it as 1 over root 10 comma 3 over root 10, whatever floats your boat. Finally, the directional derivative we're actually trying to calculate is going to be this gradient of f evaluated at 3 comma 2 dotted with this unit vector. So that's going to be our 2 comma 10 dotted with 1 over root 10 comma 3 over root 10. And then we're going to get 2 times that plus 10 times that is, let's see, 2 plus 30 is 32 over root 10. Except I made a mistake. Yeah. Well, so the directional derivative formula is specifically is a dot product. So the directional derivative of some function f in the direction of a vector u is always going to be this formula, the gradient of f dotted with u. That's just what it is. And we did kind of derive it last class, right? Where we talked about how I did the whole thing where like I found the line and the direction, and we said the line was this equation, and we did the chain rule. So we got a derivative times a thing plus a derivative times a thing, and then we saw that that was really the dot product of one vector and another vector. So that's where this formula is coming from. But I did make a mistake, and you guys, and it's not your fault, but like the 3 plus 2 times 2, I don't know how I got 10. I think I saw like
I think you did the
right, like I did 3 plus 2 is 5 times 2. I don't know what I was doing really. No, but I was really thinking 6 plus 4. I was not thinking 3 plus I was not thinking 5 times 2. So I don't know how that became 10. That should have been 7. So this should have been the vector 2 comma 7, which means everything's going to be a little bit different here. Our u is still the same, but this part's totally wrong. This part should be actually the dot product of 2 comma 7 and our direction vector 1 over root 10 comma 3 over root 10, which is equal to 2 over root 10 plus 21 over root 10. So 23 over root 10, not 32 over root 10.
Yeah, yeah, that's wrong. Is that what you're saying is wrong?
No, I'm saying this. So this is the part that's wrong here. Just the gradient of f at that point shouldn't have been 2 comma 10. It should have been 2 comma 7. This 10 here is not related to that 10 there at all. So good. It wasn't too heinous a mistake. All right. Here's a different question that's still related to this same thing. So this surface, we can maybe even draw a picture. So, or look at the graph. So what is the maximum slope at the point 3 comma 2? Well, let's see here. There's a really easy answer to this question. I just don't want to give it away too early. But the maximum slope is just magnitude of your gradient at that point. End of story. So assuming you calculate the gradient correctly, that's going to be the magnitude of the vector 2 comma 7. Yes.
just wondering. I get like the process of like when you like all like the work, but like I'm
Uh-huh.
just wondering what is gradients like, kind of like the meaning.
Right. So yeah, and this is something I remember as a student I had to remind myself of a lot of times because it's like, why is this thing the thing it is? So the one meaning of the gradient, probably the meaning that I listen to or think of the most often, it is the vector that by definition points in the direction of steepest ascent. So let me draw a little picture. And again, I'm going to go back to my favorite kind of picture because it's easy to draw. So if I'm on this, if I'm on this nice hill here and I'm at some point like this, like I'm at that point right there, the steepest ascent is the path that's going to lead me like this, right? I want to go up that way to the peak. So my gradient in 2 dimensions, right? So this surface is in 3 dimensions. My gradient vector is a 2D vector. It does not have a k component. It has an x or ij, x, y, whatever we call it, right? It has the x and the y component, but we're not thinking about moving up or down. We're saying if you try to walk into this hill, right? The direction you would walk is that way towards that middle of the hill, like in the solid ground. And then since there's a hill in the way, you would have to start walking up the hill. And that direction that's pointing inward that way, which is perpendicular to this level curve here, that direction is the direction of steepest ascent. Let's say a little bit more about it. So, and we'll come back to this question in a second because this question is not super important. But I'll point out that this is the example I've been doing before. So this is the example where our surface is f of x, y, equal to 9 minus x squared minus y squared. And the point we're looking at is the point where x is 1, y is 2, and then if x is 1 and y is 2, z has to be 4. That's the point right there. So the top view of this, I don't love my choice I'm about to make here. Let's see. I'm going to do it this way instead. So usually I'm going to draw my x-axis coming out at you and my y-axis going that way. So I'm going to take this. Yeah, and I'm going to draw it. So this is my positive x-axis. This is my positive y-axis. I know that's kind of backwards or rotated from usual, but I'm kind of just thinking of taking this xy plane and just kind of tilting it back to get that xy plane there. So here's my circle that I'm talking about. And that point right there is the point where x is 1 and y is 2. So it's like that point right there. And what we're saying is the gradient vector is the vector that has to be perpendicular to the level curve or the line that's tangent to the level curve. So here's my level curve tangent line right there, which we'll find the equation of maybe. And here is my gradient vector perpendicular to it. So let's see what we get. In this particular situation, my gradient of f is just negative 2x comma negative 2y. And at that point, my gradient vector is going to be negative 2 comma negative 4. So from here, I'm pointing, now be careful here because it's kind of oriented weirdly, right? From there, I'm pointing 2 in the negative 2 in the x direction and negative 4 in the y direction, which that seems totally plausible. Easier to see that way.
The gradient always pointing in towards the level curve.
No, so the gradient should be always pointing in the direction of which your level curves have higher values. So in this surface, where the higher you go, the smaller the circles get, right? The level curves are going to be pointing inwards because like, right, here's my level curve where C is equal to 4. And then if I let C be a higher value, like if C was equal to 5, I'd have the equation of, 5 equal to 9 minus x squared minus y squared. I would get x squared plus y squared equal to 4, a smaller circle. Whereas if my paraboloid was flipped over, my my gradients would point outwards because that would be the direction in which I'd be going up the surface. There was something else I was going to say here. I've totally forgotten what I was going to say. There was something I wanted to say. What was I going to say? There's a reason why the gradient has to be perpendicular to this tangent line and not just because like, yeah. Yeah, but like, because like, yeah, but there's some, sorry, I've just forgotten oh, right, of course, yeah. Because, right, if this is your direction vector, yeah, no, it's just because, yeah, it's because they're orthogonal. Like I can't even think of how to say it more because it's just like, it is. So yeah, the gradient vector is always, I know why, is always orthogonal perpendicular to the level curve. Okay, but there is more to say here. Because, okay, let me ask you a question. If I'm standing on this hillside and I travel in the direction of the level curve, which is always at the same elevation and the elevation doesn't change, what's the rate of change of my elevation? Right. Or in other words, the directional derivative in that direction is 0. Okay, so the directional derivative in the direction of the level curve had better be 0. Well, that's going to be the magnitude of the gradient multiplied by the magnitude of your direction vector times the cosine of the angle between them. And the only way that that quantity is going to be 0 is if this non-zero thing times this non-zero thing is multiplied by this thing, which better be 0. Or in other words, this is equal to 0 if and only if cosine of your angle is 0, which means your angle has to be 90 degrees or pi over 2 radians. That's why. Because you're moving in a direction where your rate of change is 0. I knew there was something else to say there. I was like, what is it? Okay, yeah. So, yeah. Back to this problem here. This problem seems not, but like if I was trying to find the maximum slope, it's just the magnitude of this, which is the square root of 2 squared plus 7 squared, which is the square root of 53. Pretty steep. I mean, I would think, right? If your slope is the square root of like almost 7, that means for every 1 unit you would be trying to move forward, you'd have to go up 7 units. That seems like a very steep hill. That's why you don't travel in the direction of the gradient when you're hiking. You travel in directions close to the direction of the level curve, but not exactly. Typically, depending on who has broken the trail. There was something else I wanted to say here. There's always something else I wanted to say. So some other kinds of questions people might ask is, sure, what if we imagined this surface is a ski slope? And from the point 3, 2, we would like to ski down the hill as fast as possible. What direction should we be traveling in? Well, I think it's an easy thing to intuit if you imagine what you want to think about. So if you're on this hill, the direction that's the steepest upward is the gradient. I would say not the inverse, but the negative, right? You want to turn around, right? Instead of going up as steeply as possible, you want to make a full 180 and go down as steeply as possible. And so the answer here is the negative of the gradient vector at your point. Looking back at the problem, right? So as a reminder, our gradient vector in general was, I don't remember what it was because it's been so long since we looked at this example, was y comma x plus 2y. So our gradient at the point 3 comma 2 was 2 comma not 10, 7. And so then the answer here would be the negative of 2 comma 7 or negative 2 comma negative 7. Now, I will admit this might not be technically correct in that if they ask you what direction, they usually mean give me the answer as a unit vector. So really we should say the negative of the gradient divided by its own magnitude, which is going to be negative 2, negative 7 divided by the square root of 53. Okay. Seems not unreasonable. Let's see. Okay, yeah, we'll look at one more terrible thing and then we'll move along. Yeah. So again, here's another. So I'll say again, right? The gradient points in the direction that the slope is the steepest, where it would be the most challenging to ascend your hill or mountain or whatever thing you were hiking on. Here's another very kind of contrived example, in my opinion. But hey, someone's got to make up some math textbooks. So at a certain point, we'll call it P, we are told that the gradient of f at that point is equal to 3 comma negative 4. So now the question, in what direction can we travel? In what direction? You have to write the words you say. In what direction can we travel so that the directional derivative is equal to 3? And better question, actually, first. Is there even a direction where the directional derivative will be equal to 3? So is 3 a possible output value? So is 3 even possible? What about 6? Well, here's the question that they're really asking without saying these words. How do these values compare to the maximum possible value of the directional derivative? Well, they told us what the gradient was, right? So we know that the maximum value of the directional derivative is the magnitude of the gradient. But the magnitude of that gradient is the square root of 3 squared plus -4 squared, which is 5. So 3 is totally possible, but 6 is not. So yes to 3, no to 6. Interesting, I think. We generally assume that the surfaces we're looking at are continuous, right? Like it's not like some weird surface with weird discontinuities. But basically, if your directional derivative can be as big as 5, that means you could get any value between 5 and -5. Right? If you're standing on a hill and it's steepest this way with a slope of 5 and steepest that way with a slope of -5, because you just turned around, so the slope is changed from positive to negative, then you should be able to get every value in between by turning to the appropriate direction. So the question is, how do we find the direction? So we're trying to figure out the direction so that DUF, which is your gradient vector dotted with your unit vector, which is your 3 comma -4 dotted with the components of u, let's call them u1 and u2. We want that to equal +3. Well, there's one really easy answer to see. I bet you all can figure out a choice of u1 and u2 so that this dot product was equal to +3. Don't say it out loud yet, but just think about it. There's a really, really easy thing to pick for u1 and u2 so that 3 times something plus some -4 times something is equal to 3. It's going to be u1 equal to 1 and u2 equal to 0. So one vector that will work is the vector 1 comma 0. Sometimes you can just guess a thing and get lucky, depending on what's been written, but it's not the only answer. Interesting, yeah. So, oh, sure, okay, fine. So let's talk about this. So we want this directional derivative equal 3. So we have kind of two equations, really. We have our dot product equation. Sorry, you can't see that, but I'm referring to. So we have this 3 comma -4 dotted with u1 comma u2 is equal to 3, which becomes the equation 3u1 minus 4u2 equal to 3. And we just happen to notice that u1 equal to 1 and u2 equal to 0 works, and that 1 comma 0 is a unit vector, right? That is an important factor. The unit vector we're using has to be a unit vector. And 2, there's another equation. U has to be a unit vector, meaning the magnitude of u had better equal 1, meaning the square root of u1 squared plus u2 squared had better equal 1, or squaring both sides, u1 squared plus u2 squared is equal to 1. So this is an annoying system of equations to solve, but it is solvable. We're going to take, oh, interesting. Sorry, the notes I'm looking at, the person solving this does it a vastly different way than I'm going to do it, which is totally fine. Wow, that looks terrible. I'll show you guys this in a second, but let's do this a different way because I think that's, well, we'll see. This might be terrible too. Let's find out. So I'm going to solve one of these for you, I guess. I think. No, you're like, no. What would you do?
Oh,
Okay, so yeah, it seems terrible. I'm going to isolate u1, so I'm going to say 3u1 equals 3 plus 4u2, and then divide by 3 to get u1 equal to 1 plus 4/3 u2, and then slot that in right there. So then I have 1 plus 4/3 u2 squared plus u2 squared equal to 1. Multiply the whole thing out. 1 plus 8/3 u2 plus 16/9 u2 squared plus, u2 squared equals 1. At least the ones cancel. That's a benefit. Yeah, Yeah, the ones can't. I was like, that means I'm gonna get U2 equal to 0, which I totally should because 1, 0 was one of my vectors that worked. Great. So combining things together and factoring out a U2, I have 16 over 9 plus 1 is 25 over 9. So that's going to be factoring out a U2. I have U2 times 8 thirds plus 25 over 9 U2 equal to 0. So either U2 is equal to 0 and U1 is equal to 1 plus 0, or much less conveniently, U2 is equal to negative 8 thirds divided by 25 ninths, or negative 8 thirds times 9 over 25, which simplifies to negative 24 over 25. And then plugging this back in over here, if that's my U2, then U1 is going to be 1 minus 4 thirds times negative 24 over 25. That looks bad too. Yeesh. I feel like it should be 7 over 25. Let's see. That cancels with that. That's going to be 8. Yeah. You get 1 plus 4 times 8 is 32. I feel like I'm making a mistake. Oh, I knew I was making a mistake somewhere. That should be a plus sign, not a minus sign. There we go. So you're getting, scratch that, 1 minus 4 times 8 over 25, which is negative 7 over 25. So your other vector is negative 24 over, sorry, not that. Your other vector is negative 7 over 25, comma, negative 24 over 25. Interesting. And looking at the work Grant did when he did this problem, whew, it's way worse the way he did it, I feel like. The way he does it, you have to know like some, in my opinion, obscure trig identity. Let me show you. If you're curious, here's what it looks like. So here's what Grant did instead. He said, here we're going to do the other. So the directional derivative is the gradient magnitude, which was 5, times the magnitude of our unit vector, which is 1, times cosine of theta, which we don't know the angle as we're trying to find kind of, equals 3. And then we solve for cosine equal to 3/5. And then you do, yeah, I feel like, and then you use this, because it's not that obscure of a trig identity, but like, diff. Right. I don't think it's, I mean, he comes up with the right vector, although his vector was different because of, he was actually doing a slightly different problem. But yeah, that seems worse to me. This is just in one of his handouts. Yeah. All right. That's fine. Let's move on. Because really, you can kind of keep just making all sorts of problems. And we can certainly come back to the gradient and directional derivatives, but I think it's much more fun to talk about finding and classifying extrema of functions of two variables. So this, I believe this is section 14.7. Finding and classifying extrema for functions like f of x comma y. So let's just do an example. So let's say our function f of xy is equal to 3x cubed plus xy squared minus 9x squared minus y squared. So in a similar way to 21a when we found critical values by taking the derivative and setting equal to 0, same kind of idea here, except it's both partial derivatives equal to 0. Here's why. If you're trying to find where you have a relative maximum or a relative minimum or a saddle point, well, think about it this way. If you have like a paraboloid like this, the relative maximum is right there. And the tangent plane is flat. The derivative in any direction is 0, specifically in the x direction and the y direction. Fx is equal to 0 and Fy is equal to 0. So when you're trying, and that would also be true whether it was a relative maximum or a minimum or a saddle, that at one of those 3 types of points, your tangent plane is parallel to the ground. meaning that the derivative in every direction is going to be 0. Uh-huh. We are going to use that as well, yes. Wait, say that one more time. No, so we're going to set f, we're going to find the first partial and set them equal to 0. Just like in 21A, you'd set the first derivative equal to 0 to find where you have relative extrema. So we're going to set fx, which is 9x squared plus y squared minus 18x equal to 0. This is gonna be great. And you're gonna set fy, which is y squared minus 2y equal to 0. Okay, here's what I really should have said. You know what we're setting equal to 0? The gradient, right? The gradient is the vector of partial derivatives. And you're setting the gradient, right, equal to 0. Because you want to find the point on the surface where the directional derivative is 0 for any direction, which would mean the gradient would have to be 0. The 0 vector, right? Because again, right, your directional derivative is the using the other version, the magnitude of the gradient times the magnitude of your direction times cosine of theta. Well, if we're trying to make the directional derivative 0 in every direction, well, this is going to be 1. This isn't always going to be 0. The only way to make this part always 0 is if the vector is the 0 vector. So that's what's happening here. It's good to think about it this way, I think. But let's go back to this. So solving this system of 2 equations and 2 unknowns, my words of advice are look at the equation that looks easier to deal with first. To me, that seems like the second equation. If I look at the second equation, I'm setting y squared minus 2y equal to 0. I can factor out a y and get y times y minus 2 equal to 0. So I'm either getting y equal to 0 or y equal to 2. I should say I'm getting half of a critical point. Something comma 0 and something comma 2. But I have to find the other coordinate as well. So that's when I'm going to have to use my other equation. So for y equal to 0, I'm going to take this other 9x squared plus y squared minus 18x equal to 0 and plug in 0 for y. I'm going to get 9x squared plus 0 minus 18x equal to 0. And then we solve that in whatever way we can. I'm going to factor out a 9x. I'm left with x minus 2. So if y is 0, I'm either going to get x equal to 0 or x equal to 2. Meaning my 2 critical points so far are 0, 0, and 2, 0. And then we'll look at y equal to 2. So if y is equal to 2, we're going to get 9x squared plus 4. Sorry, I feel like I'm making a mistake. Do you feel like I'm making a mistake? It's fine. Oh, I did make a mistake. Sorry, apologies. Geez, James. I made a mistake with my fy. It shouldn't have been y, it shouldn't have been just y squared. This should have been boo. Boo. Sorry. Terrible. Let's try this again. F of xy was 3x cubed plus xy squared minus 9x squared minus y squared. And let today be an extra lesson in being extra careful when you're taking these derivatives. So my fx was correct. It was 9x squared plus y squared minus 18x. My fy was not. My fy should have been x times 2y minus 2y. So I actually, after factoring this, should get 2y times x minus 1 equal to 0, meaning I'm either getting y equal to 0 or x equal to 1. I knew this example had the thing I wanted to happen. And the reason I really like this example is because I want to make it extra super clear. 1, 0 is not a critical point. Because we need to find a point that makes both of these equations equal to 0 at that same point. And if you plug in 1 for x and 0 for y, you get 9 plus 0 minus 18, which is not equal to 0. So each of these are going to lead to more critical points. So we take y equal to 0 and plug it into the first equation. We're still going to get 9x squared minus 18x equal to 0. And we're going to get 9x times x minus 2 equal to 0. So we still get x equal to 0 and x equal to 2. And so we end up getting 0, 0, and 2, 0. But then if we plug in x equal to 1, we're going to get 9 plus y squared minus 18 equal to 0. So we're going to get y squared equal to positive 9. So y is equal to plus or minus 3. So my other two critical points are 1 comma 3 and 1 comma negative 3. Say that one more time. All of them. I know it's not a nice answer, but it's what is actually being asked. So it could be as few as 0. There could be no critical points, or there could be 4 or 5 or 6. 4 is often kind of the upper limit on these problems, but you could literally have an infinite number of critical points actually. Right, not very nice, but possible. But usually 2, 3, 4, 5 is kind of. But I mean, so really your job is to do what we've done here and find your solutions to one equation and then utilize those to find the corresponding other value in the other equation. And then we have to classify them, right? So just like in 21A, your critical points could be a maximum or could be a minimum or could be neither. In 21C, you could have a maximum, a minimum, or a saddle point or inconclusive result. So how do we figure this out? Well, we have to calculate something. Most people usually call it capital D. So to classify these, to classify each critical point, we calculate D equal to the second partial of f with respect to x times the second partial of f with respect to y minus the mixed partial squared. This is analogous to, kind of analogous to the second derivative test in 21A, where instead of using the sign chart to classify whether you have a maximum or minimum, you say, okay, here's my critical point, and if the function is concave down there, it's a maximum. And if the function is concave up there, it's a minimum. So here's what we're going to do. Let's start plugging. Oh, let's maybe find this thing before we start doing the thing. So here in this case, again, remembering that our function, no, let's not remember. Let's just look instead of remembering. Looking back and seeing that our function was that, we can easily write down our second partials. So fxx is going to be 18x minus 18. Fyy is going to be 2x minus 2. And fxy is going to be 2y. Or fyx is going to be 2y. I would highly, highly, highly recommend not multiplying this out. Thank you. So don't multiply or really simplify at all your fxx and your fyy. So now we're going to plug in each critical point. So plugging in 0, 0 first, we're going to get 18 minus 0. Sorry, not 18 minus 0. 0 minus 18 times 0 minus 2 minus 0 squared. And this is equal to a positive number. I don't really care what number. I just care that it's positive or negative. Specifically here, it is equal to positive 36. So if D is positive, it means we either have a maximum or a minimum. So D positive means you have a max or a min. How do we know which? By looking at the second derivative. So I'll point out here that your fxx is negative. If your second derivative is negative, that means we are concave down, which means we have a maximum, right? So fxx being negative, you're concave down, you have a max. if we plug in the next critical point, 2 comma 0, same idea. We have 18 times 2, which is 36 minus 18. 2 times 2 is 4 minus 2, minus, again, 0 squared. This is also equal to positive 36. But in this case, my fxx is positive, which means we are concave up, which means we have a minimum. Usually, how do I say this right? So I'll point out for D to be positive, for this quantity to be positive, fxx and fyy must have the same sign. Because you have something times something minus a number squared. The only way you can be positive when you're subtracting a number squared is if the original thing was positive. And the only way that this product is positive is if both things are the same sign. So that's why we only ever check either fxx or fyy. Because if your D is positive, it's a guarantee that they're both the same sign. So you don't have to check both. You can check either one though. Okay, let's look at the next ones. Let's plug in 1 comma 3. So D of 1 comma 3 is equal to, let's see, 18 minus 18 is 0. I don't really care what the other part is, but it's also 0. Minus 2 times 3 squared, that's going to be negative 36. And if D is negative, saddle. And in a similar way, if we plug in 1 comma negative 3, we're also going to get a saddle. Because it's still going to be 0 times 0 minus 2 times negative 3 squared, which is still negative 36. So we still have a saddle. I do think it is worthwhile to actually see what this thing looks like. I mean, I usually think that, so, no surprise. But let's actually graph it here real quick, and then we'll call it a day. Look at my function again. So we have, I'll do it here real quick. So we have f of xy equal to 3x cubed plus xy squared minus 9x squared minus y squared. And we zoom out a bit. Maybe we zoom out a bit. Am I zooming out? I think I'm zooming in. Sorry, 1 second. There we go. Sure. Oh wow, you're wild looking. Maybe look at this. Okay, okay. I think we can kind of see something helpful here. So you can, okay, if we zoom in, oh geez. You can kind of see like right there's a saddle point, and right there's a saddle point, and right there's a relative maximum. It's kind of hard to see though. I'm not gonna lie. I'm having a hard time seeing it myself. But if you plug in the point like say 0 comma 0 comma 0, oh yeah, there's a maximum right there. And if we plug in, what was another point we had? What was it, 1 comma 3? Yeah. 1 comma 3 comma, what do you get when you plug in 1 and 3? You get 3, ooh geez, you get 3 plus 9 is 12, minus 9 is 3, minus 9 is negative 6. So there's your saddle point. Right there. It's a minimum in one direction and a maximum in another direction. No, not that there couldn't be an inflection point for functions in 3 dimensions, but literally it's like your classic saddle where it's a minimum in one direction and a maximum in another direction. Like an actual like saddle, like you would put on a horse, right? It's like in the direction of the horse, it's going this way, and the direction of like where your legs are going over, it's going that way. So it's a saddle. It's a minimum in one direction and a maximum in another direction. Or if you've ever been hiking, you hike up to a saddle point on your hill. You're going up, and then you say, oh, I can either go over the hill, or I can turn right or left and keep going up another direction. It's a minimum in that direction. It's a maximum in that direction. All the saddle. Or it's also called like a hyperbolic paraboloid or something. It's a saddle. All right. Have a great weekend. I'll see some of you all next week. I imagine some of you might be going places for Thanksgiving, but I'll see whoever's here, which is always true.
So like this whole thing that you're talking about.
Sure. So what I was saying was, so if you travel in the direction of a level curve, right?
Okay.
So if you're on a level curve, or specifically, let me stop this here. Level curves are the curves where the elevation never changes.